Hello, am I audible?
Hello, sir. Yes.
Mehreen, any doubt from last class?
No, sir.
Okay. In last class, we have done isobaric process. Next process is isochoric, or it is also called isometric.
So how many pages should I leave since I have not joined last class?
Just 1 minute. You may take a screenshot if you want to from this part. Done?
Yes, sir.
This one.
Yes, sir. 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 Yes, sir.
That's it. Done?
Yes.
Now the next process is isochoric or isometric. It is also called Gay-Lussac's law. The process which is carried out at constant volume is called isochoric or isometric. The process which is carried out at constant volume So in this part, volume is constant. So change in volume will be 0. According to ideal gas equation, PV is equals to nRT. So if volume is constant, so pressure and temperature will be directly proportional to each other. So we can say pressure directly proportional to temperature. So P1 divided by T1 must equals to P2 divided by T2. This will be termed as equation of state for this isochoric or isometric curve. Now, next we have to calculate specific heat for this particular process at constant volume. So molar specific heat at constant volume. So if you compare this particular equation according to equation of or generalized equation of state, PV to the power x or P to the power 1 by x times V. Since in this part V is to be constant, so x will be infinity. So put the value of x to be infinity. According in general expression of molar specific heat constant, that was R by gamma minus 1 by R minus x minus 1. So if you put the value of x to be infinity, 1 by infinity becomes 0. So this entire term for this process will become 0. So this will be termed as CV. So it will be equals to R divided by gamma minus 1, or in terms of degree of freedom, it will be F multiplied by R divided by 2. Mehreen, is it clear?
Yes, sir.
Now, using this, if you have to plot graph between pressure versus volume, similarly, volume versus temperature, and pressure versus temperature. This is pressure versus volume, volume versus temperature, and pressure versus temperature. This will be also termed as indicator diagram related to this process. Since in this part, volume is constant, so it will give you a straight line like this in increasing direction. In second part, volume is constant, so it will be a straight line. And third curve, using ideal gas equation, we can write PV is equals to nRT. Since this particular curve is between pressure versus temperature, so move this temperature to left side and volume to right side, so you'll get this expression. This quantity will be perpendicular by base, which will define slope of this particular curve. And since these two are directly proportional, so graph will be straight line like this. So if you have to relate slope of this particular graph, so slope will be inversely proportional to volume. So greater the slope of pressure versus temperature, it will have smaller volume. So Maya, is it clear?
Yes, sir.
Okay, just write it down to this part. You will have written?
Yes, sir.
Yes, sir.
Now, on the basis of this pressure versus volume curve, first we have to calculate slope. So this particular line is perpendicular with x-axis. So inclination would be 90 degree. So first is slope of pressure versus volume. So dP divided by dV, which will be tan theta, tan 90 will be infinity. So in this case, it will be infinite. Related to this slope, we have to calculate bulk modulus. So bulk modulus beta equals to dP divided by dV with negative sign times volume. Since dP by dV is infinity, so this entire term will be infinite. So you'll say this system will behave as perfectly rigid system. So it will behave as perfectly rigid. Now next, according to this curve, we have to calculate amount of work done. So work done is area under pressure volume curve. So for this part, it is just a line. There will be no area inscribed for this particular term since volume change will be zero. So work done in this case will be zero since change in volume is zero. So if you apply for first law, dq equals to du plus dw. Since in this part work done is zero, so the total amount of heat supplied or ejected must be equals to change in internal energy. So heat equals to change in internal energy. So it will be equals to N times C delta T, or it will be equals to N gamma dt divided by gamma minus 1. Mehreen, is it clear?
Yes, sir.
Okay. Now there will be questions related to this part. First, write it down. You all are done?
Yes, sir.
Saifullah, done?
1 minute. Yes, done.
Now there will be exceptional theoretical question related to this concept. Why tire of vehicle got burst after long drive or in long drive. You'll say volume of that particular vehicle will be constant. So at constant volume, pressure and temperature will be directly proportional to each other. Tire or vehicle or that particular wheel on traveling across a road get in contact with surface, due to which there is some friction in between tire as well as a road, which will generate some amount of heat. And that heat will tend to increase the temperature. And since temperature is directly proportional to pressure, so as a result, pressure inside that tire will increases. So if you are going for a long drive, so pressure will become so large, it will be capable of bursting that particular tire. So to overcome this particular process, we use some different gas filled in that tire, which may take longer time to get heated and to increase its pressure. So we generally use nitrogen gas filled for long driving. Is it clear?
Yes, sir.
Sumaya, any doubt?
No, sir.
Okay. So you will say during motion due to friction of road, heat get produced, which tends to increase temperature as well as pressure. And this pressure will capable of bursting tire for long drive or on long drive. Next will be why cooking in pressure cooker is so fast. Mamuna, any clue?
Because of the pressure in the pressure cooker.
Since in this pressure cooker, volume will be constant. So again, pressure will be directly proportional to temperature. So the air enclosed within that particular pressure cooker will generate more pressure, and on increasing more pressure, it will tend to increase more temperature, and hence it will increase rate of cooking fast. Okay. Okay, just write it down, these two terms. You all have written?
Yes, sir.
In this part, you'll write at constant volume, the air enclosed within cooker will increases temperature, hence cooking becomes fast. Now, on the basis of these two different processes, one was isobaric and this was isochoric, we have to define a relation that is called Meier's relation. So what do you mean by Meier's relation? It simply defines the relation between Cp and Cv. So let me derive you a relation between Cp and Cv, and they will ask you which of these two is greater and why. This will be most important question for your upcoming examination. First, you'll say, let's say we have a container. Its piston is fixed, and in this part, piston is in movable state. So this is the case of constant pressure, and this is a case of constant volume. So first, at constant volume, change in volume is zero. So the amount of heat supplied to this particular system can be utilized only in changing internal energy. But in case of constant pressure, amount of heat supplied to this particular system is utilized in changing internal energy as well as doing some work. So we have to relate Cp and Cv related to this process. Let me give you some numerical value related to this process. Suppose in first part, you have applied 10 joule energy, heat energy to this particular system. So how much will be change in internal energy in this process? It will be just 10 joule, since there is no any other process. So just total amount of heat supplied will be equivalent to total change in internal energy. But in second part, if you have supplied 10 joule of amount of energy to this system, some energy may be utilized in doing some work to expand this particular system from some initial point to some final point. So let's say 3 joule will be utilized in doing work, and rest of the 7 joule is to change external energy. Is it clear?
Yes.
So if you have to increase internal energy so that it becomes 10 joule, which is comparable to this part, what we have got for constant volume, you must need to increase this much amount of heat supplied. So let's say this particular quantity is increased to from 10 joule to some 12 joule, 14 joule, 15 joule, and something more. So initially for 10 joule, 7 and 3. So if you have applied 14 joule, this will become 10, and let's say this will become 4. So if internal energy for these two processes is equal, so you must need to apply large amount of heat at constant pressure as compared to constant volume. Since at constant pressure, some amount of energy may be transferred for doing work as well. So you must need some extra amount of heat supplied at constant pressure as compared to constant volume, so that change in internal energy for both these two processes becomes equal. Is it clear, Safullah?
Sir, please explain again.
Okay. In both these two processes, we have to create equal change in internal energy. So initially, suppose for constant volume, you have applied 10 joule heat to the system. How much will be change in internal energy for this process? You will say 10 joule. There will be no any other process for which this heat will evolve or this heat will used up. So the total amount of heat supplied in this process will completely transferred in changing internal energy of this particular system. But in second part, if you applied only 10 joule, this will be utilized in two different processes, one to change in internal energy and the other to do some useful work. Since this particular piston is movable, so the amount of heat supplied may be utilized in changing internal energy as well as work done both. So if you have to use increase this internal energy from 7 to 10 joule so that this part and this part becomes equal, you must increase this heat supplied to the system from 10 to 14. Is it clear?
Yes, sir.
So we can say from both these two parts, at constant pressure, amount of heat required will be always greater as compared to constant volume, so that to have equal amount of change in internal energy. Is it clear?
Yes,
Yes.
sir.
Okay. That's why Cp is always greater as compared to Cv. So you'll be asked why Cp is greater than Cv. So you'll say at constant volume, amount of heat supplied to the system is utilized in changing internal energy only. But at constant pressure, heat supplied is utilized in changing internal energy as well as doing work. So to change internal energy by same amount, more heat will be required at constant pressure. Hence, Cp is greater than Cv. Mehreen, is it clear? Sumaya, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Saifullah, done?
No, so wait. Yes, I finished.
Okay. So we have to derive this particular relation mathematically as well. So you'll say first, at constant volume, since there will be no work done, so amount of heat supplied to the system must be utilized in changing internal energy. So it will be N times CV dt. Let's say this is equation first. At constant pressure, dq equals to du plus dw. We may write this dq as N times Cp dt. du is N times Cv dt, and work done is pressure times dV. So as ideal gas equation, PV is equals to nRT. Since in this part, pressure is constant, so differentiate with respect to temperature. Since P is constant, so it will be remain outside. V on differentiating, it will be dV by dt equals to N is constant, R is constant, and T on differentiation, it will be just 1. So on rearranging this equation, you will get P dV equals to nR dt. Put this expression in the upper part for work done. So N times Cp dt will be equals to N times Cv dt, and in place of PdV, nR dt. So N and dt will cancel out from both sides. So you're left with Cp is equals to Cv plus R. This relation between molar specific heat constant at constant pressure and molar specific heat at constant volume is termed as Mayer's relation. Mehreen, is it clear?
Yes, sir.
Okay, just write it down. Abdul Wahid, any doubt? You all have written?
Yes, sir.
Safullah, done?
Yes, sir.
Okay. Next is isothermal process, which is also called Boyle's law. It states the process which is carried out at constant temperature, the process which is carried out at constant temperature is called isothermal process. So T is constant, delta T will be 0. So according to this equation, PV is equals to nRT. Since T is constant, so pressure and volume should be inversely proportional to one another. So P1 V1 must equals to P2 V2 will be equation of state for this part. Next, according to generalized equation, P V to the power x is equals to constant. So product of these two terms should be constant. So x will be 1 for this case. So molar specific heat at constant temperature C equals to R divided by gamma minus 1 minus R divided by x minus 1. And since x is 1, so 1 minus 1, 0, 1 upon 0 becomes infinite. So you'll get infinite molar specific heat for constant temperature. Now, related to this, we have to plot curve between different thermodynamical variables. First, between pressure versus volume, between pressure versus temperature, and third, volume versus temperature. Since pressure is inversely proportional to volume, so graph will be a rectangular hyperbola like this along this direction. So in this part, pressure is decreasing, volume is increasing. In second part, temperature is constant. So graph will be straight line and pressure will be decreasing. In third part, temperature is constant. So graph will be straight line, but in this part, volume will be increasing. Sumaya, any doubt?
No, sir.
Okay, just write it down to this part.
Sir, please explain the graphs again.
Okay. Since we have pressure versus volume related as this, pressure is inversely proportional to volume. So for this inverse relation, graph will be rectangular hyperbola like this. If volume is increasing, pressure must be decreasing. And if volume will be decreasing, pressure must be increasing, or vice versa. So the curve related to this will be rectangular hyperbola. In second part, since temperature is constant, so for constant, it will be a straight line parallel to opposite coordinate. Since there will be no change in temperature, so it will remain same at all point. Similarly, in the case of this as well, but we are dealing for expansion of gas for which volume will increase. So volume will increase and as a result, pressure will decrease. So that product of these two terms will be always constant. Okay, Saifullah, is it clear?
Yes, sir.
Okay.
Done, sir.
Marine, you have written?
Yes, sir.
Saifullah, done?
Yes.
Okay. Now, using this, for first graph, pressure versus volume, we have to calculate slope. So first is how to calculate slope of pressure versus volume graph. You'll say relation between these two terms according to ideal gas equation, pressure into volume equals to constant. So differentiate with respect to volume. So using product rule, we can say differentiation of first quantity multiplied by second term plus differentiation of second quantity multiplied by first term. So differentiation of volume in this case will be just 1. And since in denominator, in right hand side, we have some constant value. So on differentiation, it will give you just 0. Move this P to right side. So dP by dV equals to minus of P, and this volume on moving to other side will be in denominator. So this will define you slope of this particular curve. Related to the slope, if you have to calculate bulk modulus, that is beta, it is equals to dP by dV multiplied by V. dP by dV is minus of P by V, so minus minus plus P by V multiplied by V. V and V cancel out, so you get just P. So beta for isothermal process is equal to pressure of system at that given condition. Next, we have to calculate work done for this process. Let's say initial volume of gas will be at this point, final gas at this point. So work done is P multiplied by dV integration. Since in this part, these are all variable quantity. So using ideal gas equation, you'll say PV is equals to nRT. So P is equals to nRT divided by V. Put this pressure as this in terms of volume, in which nRT is constant. So we're left with dV divided by V, which is going from some initial volume to final volume. And on integrating this work done, you will get just W. Is it clear to all of you till this part, what I've done?
Yes.
Sumaya, is it clear?
Yes, sir.
Okay. Now in this part, we have 1 divided by V. So on integration, it will give you log or natural log. So it will be nRT natural log V having upper limit V final, lower limit V initial. Now on putting the limit, you will get nRT ln V final minus ln V initial. Using the property of log m minus log n is equals to log m by n. So it will be equals to nRT ln V final divided by V initial. So this will be your final expression of work done. So in your school examination, you'll be asked to derive expression of work done for isothermal process, since this is the only derivation in this entire chapter. Okay. Any doubt in this part?
So explain from work done.
Okay. According to the relation, work done equals to P times dV. And since in this part, no one in these two terms is constant. Both are variable depending upon one another. So I have to replace one of them in terms of other. So I've just used ideal gas equation. PV is equals to nRT. So from this part, P will be equals to nRT divided by P. So I have replaced this P in terms of this part and put in place of P as this. So it will be nRT as constant. So keep it outside. So we're left with dV divided by V, which is similar to 1 by x. So on integration, it will give you just log of x or natural log of x. integration dx by x will be ln x. First property which I've used. Second property of log m minus log n. In this part, we are using ln, that is natural log. So it will be ln m minus ln n, which is equals to natural log m by n. I've just used these two property in this part. Safurla, is it clear now?
Yes, sir.
Okay. Just write it down.
So please go up.
Furthermore, you'll have done. Saifullah, done?
Yes, sir.
Okay. The indicated graph between pressure and volume for isothermal process is find first pressure at point B and second work done during process. From A to B. Just use the above equation for equation of state for this isothermal process. That was P1 V1 equals to P2 V2. We have P1 V1 and V2. For this and this part, you will guess first expression. Try to find this. Just 1 minute. Convert this to 8 centimeter cube. Any problem while solving this? Memo now?
No, sir.
Okay. Good memo now. 1 atm equals to 10 to the power 5 Pascal, and 1 centimeter cube equals to 10 to the power minus 6 meter cube. Good, Safullah. So for P1 at point A, we have pressure 5 atm. 1 atm is 10 to the power 5. V1 is 4 centimeter cube. So we may write 4 in 10 to the power minus 6 equals to P2, which we have to calculate. Volume at point B is 8 centimeter cube, 10 to the power minus 6. So on solving, pressure at point B will become 2.5 atm or 2.5 into 10 to the power 5 Pascal. Sumaya, is it clear?
Yes, sir.
Okay. Now the next process is we have to calculate work done on going from A to B. According to the above relation for work done equals to nRT ln V final by V initial. Since in this entire process, there is no any information about N temperature. So how to find the value of these two terms? So let me give you a hint. According to ideal gas equation, you will say PV is equals to nRT. So instead of finding the value of this part, just place the value of these two terms for any one of the coordinate, either for coordinate A or either for coordinate B, it will give you same result. So this particular quantity will be equivalent to PV ln V final divided by V initial. Safullah, is it clear?
Yes, sir.
Now let me calculate for coordinate A. At point A, we have pressure 5 into 10 to the power 5 Pascal and volume is 4 into 10 to the power minus 6. ln final volume by initial volume. Final volume is 8 into 10 to the power minus 6. Initial volume is 4 into 10 to the power minus 6. So on solving, 5 into 4, 20. 10 to the power 5 minus 6 minus 1. ln 10 to the power minus 6, 10 to the power minus 6 will cancel out. 8 divided by 4, it will be just 2. So 20 into 10 to the power minus 1, it will be 2 ln 2. This is equal to 0.7. So it will be 2 into 0.7. It will be 1.4 joule. In your examination, they will give you the value of ln, which will be used in the expression. So ln2 is 0.7. Mamuna, any doubt?
No, sir.
Okay.
Done, sir.
So Fulla, done?
Yes, sir.
Okay. Now, using first law, you'll say dq equals to du plus dw. Since in this entire part, there is no change in temperature, so this particular quantity will be 0. So the amount of heat supplied to this particular system will be equivalent to work done during this process. So dw will be 0. So dq equals to dw, and it will be equals to nRT ln V final divided by V initial. But this internal energy will be or will have some value in case of change of state for water. So you'll be asked to calculate change in internal energy during fusion and during vaporization. So how you'll calculate? First, for fusion, dq equals to du plus dw. dq is amount of heat supplied to this particular system. So in case of fusion, that is from solid to liquid change, it will be termed as latent heat of fusion. So this will be equals to mass of ice times latent heat of fusion equals to change in internal energy plus work done. And work done in this case will be P times change in volume. So you will have change in volume at some given pressure, mass of ice, latent of ice. Using this expression, you will be able to calculate change in internal energy for this particular process. Similarly, in case of vaporization, that is changing from liquid to vapor state, amount of heat supplied will be mass of water, latent heat of vaporization. It will be du plus P times dV. So using this, you will be able to calculate change in internal energy. So in this entire isothermal process, only in the case of fusion and vaporization, they will have some internal energy, but rest of all process, change in internal energy will be 0. Is it clear?
Yes, sir.
Okay, just write it down.
Sir, it is the first law of what process, sir?
First law of thermodynamics.
Does it come under Boyle's law?
It will be valid for all different processes, but in this part, we are doing for isothermal process. That is for Boyle's law.
Okay.
You all have written? Saifullah, done?
Yes, sir.
Sumaya, any doubt?
No, sir.
Okay. Suppose 1 gram ice is melting into water at 1 atm, for which change in volume (50 centimeter cube). Find change in internal energy during this process. Latent fusion constant for ice is 80 calorie per gram, and 1 calorie equals to 4.2 joule. So first try to calculate energy in terms of calorie and then convert it into joule. Put all the values in the above part and try to find.
So what is Mi in the above equation?
Mass of ice, which is 1 gram. Pressure is 1 atm, 10 to the power 5 Pascal. Change in volume is this much. Let me solve. We have mass 1 gram multiplied by latent heat of fusion, that is 80 calorie per gram. So this entire term will be in terms of calorie. So if you have to convert in terms of joule, just multiply this expression by 4.2. This will be equals to du plus pressure. We have 1 atm, 1 into 10 to the power 5, and change in volume is 50 centimeter, 10 to the power minus 6. So 8 into 2, 16, 8 into 4, 32 plus 1, 33. So it will be 332 joule equals to du plus 10 to the power 5, 10 to the power minus 6. It will be 10 to the power minus 1. So it will be just 5. So change in internal energy during this process will be 332 minus 5. It will be 327 joule. Saifullah, is it clear?
Yes, sir.
Sir, 80 into 4.2 is 336, right?
Oh, just 1 minute. So it will be 331. Good, Mamuna. Sumaya, is it clear?
Yes, sir.
Okay. Shab, any doubt? You all have written?
Yes, sir.
Saifullah, done?
Yes, sir.
Okay. This is all about isothermal process. Next is adiabatic. The process which is carried out at constant heat is called adiabatic process, and there is no specific name for this particular process. So you'll say the process which is carried out at constant heat. So dq will be 0 or q will be constant. Now we have to derive its specific or equation of state, or let me write it. It will be PV to the power gamma equals to constant in terms of pressure volume. If you convert this relation in terms of temperature, it will give you T nRT by P nRT by V. So V to the power gamma minus 1 is equals to constant. In terms of pressure temperature, it will be P to the power 1 minus gamma, T to the power gamma equals to constant. Since this derivation is, there is no any explanation of this derivation in your course, but in some school, you might be asked to derive this particular relation and some may not. So what will I do? Should I derive this? Amuna,
Yes, sir.
should I derive this expression or should I leave this?
Leave it as it is.
Okay, good. Since it is beyond your course, or you may derive it using mathematical relation, but since it is not in your course, so let me leave it. You have to use this particular relation. That's it. We have PV, that is pressure and volume, and gamma is a specific gas ratio. So related to these two terms, we may use this expression. So molar specific heat at constant heat CQ equals to R by gamma minus 1 minus R by X minus 1. Just see this particular expression. We have V to the power gamma. So the value of X related to this will be gamma. If you put the value of X to be gamma, this expression and this expression will be equivalent to each other. So the difference of these two terms will give you 0. So molar specific heat constant at constant heat will be 0. Is it clear?
Yes, sir.
Now, graph related to this process will be between pressure versus volume, volume versus temperature, and pressure versus temperature. So using the above relation, for first part, pressure and volume, the product of these 2 quantities is constant, so they must be inversely proportional to one another. So the graph will be like this. In second part, for pressure and temperature, if you rearrange this last expression, you will get T to the power gamma divided by P to the power gamma minus 1 becomes constant. Since we have in this part 1 minus gamma and gamma will always greater than 1, so this particular ratio will be, or this particular exponential will be negative. You have to convert it into positive, so move this term to denominator, you'll get this expression. So related to this expression, you will say pressure and temperature should be proportional to one another. So the graph related to this curve will be like this. In third part, since volume and temperature is inversely proportional, so graph will be like this. And in this, volume is increasing, so temperature must be decreasing. So it will be like this. Saifullah, is it clear? How I just redraw different curve related to the above expression?
Please explain it again.
Okay. Using this first expression, you will say pressure inversely proportional to volume to the power gamma. So the graph will be rectangular hyperbola. Using this third expression, you will say pressure to the power gamma minus 1 will be directly proportional to temperature to the power gamma. Since in this part, we have 1 minus gamma, so on moving it to denominator, it will become gamma minus 1. 1 divided by p to the power minus of 1 gamma minus 1 t to the power gamma. Since on moving any quantity to denominator, its exponential will change its sign from plus to minus or minus to plus. So on moving it to denominator, it will become minus of 1 minus gamma. So -1 and minus plus gamma. So you'll get this expression. Saifullah, is it clear?
Yes, sir.
So using this, we can say pressure and temperature related to each other directly, but at some different exponential. Using this, you will say temperature inversely proportional to volume to the power gamma minus 1. So again, graph will be rectangular hyperbola. Now, in first part, since volume is increasing, so pressure must be decreasing. So in second part, since pressure is decreasing, so temperature must be decreasing. Similarly, in third part, volume is increasing, so temperature must be decreasing. Memuna, is it clear?
Yes, sir.
Okay, first write it down to this part. You all have written?
Yes, sir.
1 minute. You finished, sir.
Okay. Now, related to this part, first you'll be asked to calculate slope of this particular PV curve. So slope of pressure versus volume graph. Since we have relation between pressure volume as PV to the power gamma equals to constant. So differentiate with respect to volume. So first, differentiation of first part multiplied by second. Differentiation of second part multiplied by first. And differentiation of any constant term is 0. I've just differentiated P and multiplied V. In second part, since V having exponential gamma, so it will be nx to the power n minus 1. Using this, I have differentiated this, multiplied by P. Memuna, is it clear?
Yes, sir.
Okay. Since we have to calculate dP by dV, so move the rest of the term to right side. So dP by dV multiplied by V to the power gamma equals to minus gamma P V to the power gamma, and V to the power minus 1 will be in denominator. So V to the power gamma and V to the power gamma will cancel out. So you're left with dP by dV equals to minus of gamma P by V. So from this part, you'll be asked to relate slope of isothermal curve and adiabatic curve. So you'll be given pressure versus volume for isothermal curve as well as adiabatic curve. One will be along this and the other will be along this. Let's say this is A and this is B. So you'll be asked which of these two will be for isothermal and adiabatic. So let me define you how to define. In this part, we have calculated slope of P versus V for adiabatic process is minus of gamma P divided by V. But in last part, for isothermal process, I have calculated just see this. Slope for isothermal, it is just minus P by V. Okay. Sumaya, is it clear?
Yes, sir.
Okay. So if you have to compare, so you'll say slope for isothermal is minus of P by V and slope of adiabatic is gamma times P by V. So on comparing, you will say slope for adiabatic will be gamma times slope for isothermal. So this is the relation between slope of these two different processes. And since gamma is always greater than 1, so you will say adiabatic curve will be more steeper as compared to isothermal curve. Saifullah, is it clear?
Yes.
So adiabatic curve will be more steeper than isothermal. Mamuna, just tell me which of these two curve is more steeper, A or B?
The B1.
Good. So A1 will be isothermal and B will be for adiabatic. Mehreen, is it clear?
Yes, sir.
Okay, just write it down. You all have done?
Yes, sir.
Yes.
Okay. You may be asked for some different gas as well in terms of adiabatic curve. So you will say, since slope is directly proportional to gamma, so if you have to define for monoatomic, diatomic, triatomic, pressure versus volume, one of the curve will be at this, next will be at this, and next will be at this. So which of these curve will be for monoatomic, diatomic, triatomic? So Maya, just tell me, for which gas gamma will be maximum? Saifullah,
Yes.
for which gas gamma is maximum?
C.
No, I'm just asking for monoatomic, diatomic, triatomic. For which gas gamma will be maximum?
Triatomic.
Triatomic have maximum degree of freedom, so it will have least gamma. Okay. So in this part, the more value of gamma, it will have more steeper curve. And since monoatomic have a maximum value of gamma, so it will be at the lowest point, then diatomic, then triatomic. Sumaya, is it clear?
Yes, sir.
Memona, any doubt?
No, sir.
And next, how to compare or how to analyze which of the curve will be or which of the process will be isothermal or adiabatic, since both are inversely proportional to one another. So there is a term which is called quasi-static process, a process which is carried out very slowly, very slow. This will be isothermal, or the process which acts suddenly, it will be adiabatic. So remember these two words to define process isothermal and adiabatic. Is it clear to all of you till this part?
Yes.
So what is quasi-static process again?
A process which takes place very slowly. Okay.
Okay.
So isothermal process termed as quasi-static process. And adiabatic, which acts very fast, suddenly, abruptly. So you'll be given a gas expand abruptly to twice its volume. What process it will be? Isothermal, adiabatic. So you'll say adiabatic. You'll be asked, suppose a balloon fully inflated, if you pinch from any one side, so it may get burst and air will escape out from it. Will that air cold or hot? Mamona,
Sir, can you repeat?
suppose if a tire got burst, so the incoming air from the tire, will that air will be hot or cold?
Cold.
Why? You'll say initially in balloon and tire will have higher pressure. So on exposing to atmosphere, it will have lesser pressure. So it is going from higher pressure to lower pressure. So pressure is decreasing. And since for adiabatic process, which is carried out very fast, abruptly, so pressure is proportional to temperature. So if pressure is decreasing, temperature must be decreasing, hence the air will be cold. Is it clear?
Yes.
Saifullah, any doubt?
Yes, sir.
Okay, that's all for today. We'll continue next class. Okay?
Sir, can you go up? I was disconnected for a while.
Okay. No problem.
Thank you, sir.
Thank you. This part or before it?
Before this, sir.
This one?
Yes, sir.
Or before this?
Can you go little more? Yes, sir. Thank you.
You have taken a screenshot?
Yes, sir.
Okay. Okay, Sumaya, any doubt?
No, sir.
Okay, then we'll continue in next class.
Thank you,
Thank
sir.
you. Thank you.